Hello and welcome, everybody. My name is Avin Abel. I'm your host today. It's my physics 2211 Lab 4 Oscillations. So getting the ball rolling with our table of contents. We're going to talk about 7 things today. Not really. It's just 7 of the same things. Anyway, our introduction. In this lab, we did 2 things. Firstly, we used Tracker to analyze a video of a mass oscillating on a hanging spring. Then we created a computational model in GlowScript based on our findings from our tracker. So now getting into some of the physics principles used in this lab. So we have Newton's momentum principle, which states that net force is equal to the change in momentum over the change in time. And we can see also to the right, this is often used in tandem with our position update and our velocity update formulas. And more principles, we have our energy principles. These are very important. It's quite an integral part of the lab, honestly. Up here we can see that kinetic energy, there's change in kinetic energy plus change in spring energy plus change in gravity energy is equal to 0. That's the case for this experiment because I took the Earth to be in my system. If you took Earth to be outside of the system, then this would not be the case because gravity would be a force, not an energy. But we know that energy is not created is neither created nor destroyed, so it should all equal 0 in the end. And we can see that kinetic energy equals 1/2 mv squared, spring potential energy equals 1/2 ks squared, and gravitational potential energy equals mg delta h. So now getting into our experiment a little bit. So we wanted to track the position of the mass as it oscillated due to hanging from the spring. So apologies, I don't know how to play this video. But we can see our spring is down here, and our mass is down here, and it's hanging from the spring, and it just kind of went around in a circle like that. And then as far as our coding went, here are some of our initial conditions. We know the mass of the mass. We know the gravity constant. We know the spring constant based on the period of oscillation, and then we found the relaxed length of the spring. Then continuing our coding, here we defined the L hat, and S, and this was just to calculate our spring potential energy, which we did down here, along with our kinetic and our gravitational potential energy, and then we added those all up to get E, our total energy. And then over here, this is in our while loop, and we defined our initial energies, and then calculated our force of gravity and the force of the spring to calculate the net force. And then using that net force, we used the velocity update principle and the position update formulas, and then updated the spring position again. And then using what we found there, we come over here to the left and calculated the change in the different types of energy, and then sum them all up to get delta E, which is our total change in energy. And so what does this look like after it's played out, So here are our graphs. This is our graph of our change in energy versus time. And as we can see, this is consistent with what we would expect, as delta E here in orange stays at 0 the whole time. And like I mentioned earlier, because energy cannot be created nor destroyed, the total change in energy should just be 0 because there's no external forces adding energy into our system. So yeah, we can see that these all energies balance themselves out to 0 at any given time. Oh, apologies for being blurry. I don't know why that happened. But here are 2 more graphs between our model and our experiment of our x position versus time and our y position versus time. They look pretty consistent, which is good. So anyway, what does this all mean? So for our model system, is the energy principle satisfied? Yes, it is. As I just mentioned earlier, the change in spring potential energy and gravitational potential are opposite to one another, as well as the kinetic energy, meaning that the sum of all energy is 0. And like I just said, energy cannot be created nor destroyed, so it has to stay the same, like it did in the graph. What else does this mean? So we found that our X oscillation average was 1.61 seconds, whereas our Y oscillation average was 1.67 seconds. And there was a difference of 0.06 seconds. So this could be chalked up to a few things. It's possible that I used tracker incorrectly. It's possible that I made a typo in my code. But also, even just in real life, there are more energies than the 3 I used. things like heat, sound, and vibration all require energy. Also, air resistance was not accounted for. Um, so yeah, there are a few things that could have led up to that discrepancy. But overall, this was a pretty successful lab, and I really thank you for taking the time to listen in. Yeah, have a good one. Stay jacking it.